Yeah, okay, you can start it. It's very loud here. What do you think? How about now? Better? People in the back can hear me? Okay. Okay. It's all good? Okay, we still have 1 minute. So. I guess other people are having the same problem you had. Automatically locking doors. Okay, let's get started. So today we're going to cover whatever we didn't cover yesterday, at least a portion of it. And then we're going to jump into memory latency, which is really a critical topic. Latency is often ignored, as we had discussed in an earlier lecture, but it's really the root cause of a lot of the complexity that we have in our systems. And we should change that mindset also. There's a lot of mindset that we need to change, I think, in designing computing systems, but latency is very well known, yet it's still a problem. Okay, let's finish with data retention. Remember, we were discussing how to reduce problems that are caused by data retention issues with a focus on DRAM. But I mentioned that this issue exists in any type of memory. I will mention quickly this idea of refresh access parallelization, parallelizing refreshes with accesses so that you reduce the impact of refreshes on the accesses in terms of latency, in terms of performance. And I think this is a very nice idea in general. It was described in this paper. I'm not going to talk about this paper in detail, but what this paper does is while a refresh is going on to one subarray, you can actually do access to some other subarrays. I will talk about this paper that Giray led in the recent past, which showed essentially that you can actually do this in real DRAM chips to a limited extent by violating the timing parameters. So a lot of these ideas that were actually shown in simulation, like in this work in 2014, are possible to a limited extent in real DRAM chips by violating the timing parameters. And you've seen this before, right? With row clone, for example. In this case, you've also seen it with bitwise operations in DRAM chips. Now we actually also see it in parallelizing accesses to different subarrays. So this is actually a nice way of doing research, in my opinion. You first build the theory. The theory says you should be able to do this based on the circuit principles, on architecture principles. And then you show this in simulation. And maybe after some time, you develop the infrastructure to show that, oh, actually, you can do it in real DRAM chips with a limited capacity. Okay, so we'll talk about this hidden row activation idea. And given that this work was done in 2022, refresh actually is becoming a bigger problem, as we have discussed. There's periodic refresh, but there's also preventive refresh that happens when you have RowHammer bit flips, and you want to prevent these bit flips. And several mechanisms have been proposed, as you have seen, to refresh or preventively refresh physically adjacent rows that might be vulnerable to these bit flips if a row is being hammered enough times. This is all familiar, right? It all makes sense. So a refresh problem is becoming worse in a sense, right? Because of RowHammer. So I think we've covered this. I'm not going to go through this in detail, but periodic refresh is getting worse. And this is some projection also. At large DRAM chip capacities, you actually get significant slowdowns. This is based on some other projections, more reasonable projections than we had done in 2012, let's say. But things have changed also. You have more data points. And RowHammer, you've also seen that as DRAM chip density increases, RowHammer vulnerability worsens. And we have shown that there's real data from the field that shows that. And actually, if you do preventive refreshes, as RowHammer threshold goes down from 1024 to 64, with some mechanism, para, I believe in this case, you get a lot of slowdown because you have to ensure that you don't get bit flips. That means that if you actually get a bit flip after 64 activations, you need to do a lot of refreshes. to overcome to make sure that you don't get that bit flip, especially with a probabilistic mechanism like para. Okay, so essentially the overhead of refresh is increasing due to both periodic refreshes as well as preventive refreshes. So the idea of refresh access parallelization is to essentially enable some part of DRAM to do refresh while other parts are servicing accesses. That's the major idea, basically. And there are multiple ways of doing it. One way of doing it is changing the DRAM. Another way of doing it is basically violating the timing parameters and see what happens. Basically, GRI has found that if you activate 2 rows in quick succession that are in different subarrays in the same bank, you can refresh 1 row while concurrently activating the other row. That's the idea. You do 2 activations and in quick succession, meaning violating the timing parameters. And if these 2 activations go to different subarrays, the first activation refreshes row A while the second activation activates row B. Does that make sense? And the details are in the paper. I will not go through this in detail, but it makes sense to think about it because each of these subarrays have their own local row buffers. And while the first activation is actually bringing data to the local row buffer of subarray X from row A, the second activation enables the local row buffer. The second activation enables row B to be brought into the local row buffer as well as the global I/O, and you can read data from the second activated row, even though you cannot read data from the first activated row. You can that actually accomplishes refresh because you brought it into the local row buffer. And then once you do the pre-charge, all of the data will be written back to the rows. Okay, so that's the idea. So what's the benefit? If you look at the benefits in the baseline system, you first activate row A, which accomplishes a refresh. Refresh you can think of as an activation. And then you pre-charge it because these go to the same bank. You need to activate row B after the pre-charge of the bank is complete. And then you can start reading from row B after that point. If you use this hidden row activation, you first activate row A and then quickly pre-charge it, pre-charge the bank, and then you activate row B at the same time, almost at the same time. Is it 3 nanoseconds? Yes, okay. Those are the delays. He remembers it. That's good. Maybe I remember it too. So this way you can hide row B's activation while row A is being refreshed, or you can think of it the other way, right? You can hide row A's refresh with row B's activation. They're overlapped, essentially. And you can issue a read over here. This way you can save time using this mechanism. Okay, and Giray tested this on many DRAM chips, and he found out that on SK Hynix chips, you can actually do this. He can tell you why it doesn't happen in other chips, probably, because some of them have idiosyncratic mechanisms that don't allow you to do back-to-back activations like this, which is not nice, I think. I think DRAM manufacturers should be better at exposing things so that people actually discover these things or enable new functionality in DRAM, as opposed to preventing some experimentation with DRAM, which I think goes against their interest, but frankly, I don't know what their interests are. It doesn't seem to be being intelligent about business, for sure. even though I'm not a businessman, I can see that also. Okay, but basically, you can see that after testing this on real DRAM chips, we found out that you can get more than 50% reduction in the time spent for refresh operations. And there's a lot more detail in the paper. You can see it, or you can talk to Giray. I think this is also very interesting because we have seen similar things in simulation like 8 years ago before this paper. But now this shows that you can do it for a limited set of subarrays inside a DRAM chip. This doesn't work for all subarrays because there's some internal circuitry that we don't quite understand. And clearly you cannot easily manipulate by violating the timing parameters. But this shows that if you actually go and design the DRAM chip to do this carefully, you should be able to design it. There's no reason why you cannot. Okay, and then we designed a memory controller that essentially tries to exploit it. I'm not going to go through this in detail, but memory controller buffers each refresh request and tries to hide the refreshes that go to the same bank as accesses to the same bank. So you try, whenever you're activating a bank, you don't just activate that bank, but you also schedule a refresh that goes to a different subarray concurrently with an activation that goes to the same bank to another subarray. So you need to design a memory controller mechanism that takes advantage of this, of course, right? Okay, I'm not going to go through this, but if you do that, and if you go and simulate using RowHammer, you get significant benefits, especially on preventive refreshes, meaning if your RowHammer vulnerability is quite bad, you actually get a lot of speed up by reducing the performance impact of preventive refreshes on accesses. But even if you don't have preventive refreshes for whatever reason, periodic refreshes, by doing this on periodic refreshes, you still get significant speed up, as you can see. And there's hardware complexity analysis. If you actually do this in the memory controller, it's a small amount of logic and very little latency. Okay, so if you're interested, there's a paper. You can ask questions to Giray, or if you have a burning question, I can answer right now as well. Thoughts? Yes, do you have a question for yourself? Okay, go ahead.
Since then, we had more studies with SmileNet, and we have a better understanding of how these rows are laid out and how these subrows are organized, right? So,
yeah.
Maybe there's more to discover. I guess we can invite people to work on this kind of problems with us.
That's true. Yeah, exactly. I think as I discussed in the memory-centric computing lectures, and as we will discuss more once we talk about processing using memory, now we know actually how to activate many rows in different subarrays. And we know how the hierarchical decoder is organized. At least we have a much better understanding of it. So maybe there is a better way of doing things like this. Maybe you can do access parallelization to subarrays, which is what we're going to talk about later in this lecture, which is called Subarray-level parallelism. But that's going to be very tough, I think, without changing the DRAM. Okay. So I should also say that these issues are discussed by industry. Industry is clearly trying to improve refresh. And there are a lot of papers, well, maybe a lot is an overstatement, but there are papers in circuit level conferences that DRAM manufacturers write to optimize refresh in different ways. So they really care about it. And there's a good reason, because it's a scaling challenge, as we have discussed. That's why we started looking at it. And this is a paper that I mentioned in earlier lectures, maybe Mohammed mentioned it, that was written by Samsung and Intel in the Memory Forum in 2014. This is a nice paper. I would still recommend it to people. But if you look at this, they talk about three major challenges. VRT, we already talked about, variable retention time. And this paper also says that we add error correcting codes to handle VRT. So that part of the paper is really about error correcting codes. The second part is write latency, which I'm not going to talk about right now, but it's the subject of, let's say, the next part of this lecture on memory latency. So they care about write latency is increasing. And their solution is actually one of the solutions that we will discuss, Subarray-level parallelism. You can tolerate the write latencies by doing one access in one subarray while doing write to another subarray. And they actually evaluated and find good results. This is essentially a validation of our work that was published 2 years ago before this. But the important part, well, one important part over here is the refresh. As you can see that they say that it's very difficult to handle the refresh problem because leakage current of cell access transistors is increasing, cell capacitance is decreasing. So we need better solutions to this problem. In this paper, they did not talk about RowHammer because it was exposed 2 days after this paper was published in 2014. But I would probably add that also. But there's another interesting thing in this paper, which essentially goes along with what we have been saying for a long time, which is to overcome these challenges, they say it's very difficult to do circuit or device level solutions. We should really design controllers and DRAM together, essentially intelligent memory controllers. And also there's another interesting thing in this paper. This is the only paper that I know of where Samsung and Intel collaborated and wrote a paper. If you find something else, let me know. Usually these companies don't talk to each other without a lot of lawyers present in the room. But these guys actually were forward looking to collaborate. And I have more stories about this paper later on. Any questions? Okay, how many people read this paper? It's 4 pages. I think it's part of the homework, right? Or one of their suggested papers. I don't remember, but if not, it's in the next homework. And again, in the homeworks, you have some required papers, but you have a lot of suggested papers that are for extra credit. If you actually review those papers, you get a lot of extra credit. So the goal of this course is not to like nickel and dime you with every single grade. The goal of this course is to enable you to learn. So you can actually not worry about a lot of grading while learning. So these extra credits are all opportunities. Okay. So this is something I will not cover in detail, but I will flash some slides. As you can see, there's flash memory because we don't have, I think, time right now. But this is an issue in flash memory also. Very quickly, flash memory is, even though it's non-volatile memory, it's still charge-based memory. So there's floating gate charge, and you trap the charge in the floating gates, and then you basically sense the charge with different mechanisms. Unfortunately, charge essentially leaks through the floating gate, again using leakage mechanisms, which we will discuss later on. But this problem also becomes worse in flash memory as the charge storage unit size reduces. And as a result, retention becomes a problem. In fact, even though it's non-volatile memory, flash memory gets refreshed in real commercial SSDs because as things age, the retention becomes a bigger problem. And over time, people need to refresh flash memory. Not at the same scale as their DRAM is refreshed, but at a longer time scale. But I will flash some papers and we'll talk about them later. And one of the issues is as flash memory gets older, as you write more data, retention errors start increasing and accumulating. And this refresh starts increasing and other mechanisms to tolerate these errors in the flash controller starts increasing. As a result, you start getting performance degradations. And these are actually very well known, very well reported, which I'm not going to talk about right now. But as I said, I will flash some of these slides. So basically, charge leaks over time, and this leads to a retention error. And we have analyzed this a lot in our early and later papers. And to overcome this, you need to read, make the reads take longer, either to sense small amount of data, or you need to map the data somewhere, or you need to add ECC. So there are many mechanisms you can think of, including variable rate refresh, etc. So we have characterized these errors, and as early as 2011, the paper was published in 2012, using an FPGA-based infrastructure for flash again. And essentially, we've looked at read errors, erase errors, and program errors, which you will talk about later on, and also retention errors. Essentially, this is whether an error happens, basically, this depends on the retention time, how long you want the data to be retained in flash. And this becomes worse in a flash memory where in a single cell, you encode more bits. This is called MLC, multi-level cell, which is not the best naming perhaps, but multi-bit cell is probably another, multi-bit encoded cell is probably a better name. But essentially, you use the same voltage range and you chop up the voltage range to smaller intervals so that you can encode more bits, like 2 bits, 3 bits, 4 bits, etc. And if you do that, then the width of the voltage window, all voltage range, reduces. That is allocated to a particular encoding, and the probability that you will get when essentially you get a charge loss, the probability that one encoded bit will shift into the domain of another encoding in the voltage levels actually increases. Okay, as I said, we did a lot of studies over here. This is just to whet your appetite, if you will. So this program erase cycle is how many times you have written to a particular location in flash memory, and you can see that this raw bit error rate that we observe in flash memory increases as you keep writing to flash memory. This is the endurance problem that we see. And you can see that the biggest errors are really the retention errors. So most of the errors that are responsible for the raw bit error rate that we see, even when the flash memory is young, meaning it has not been written too much, is still retention errors, as you can see. So if you want to retain data for 3 years, you cannot do that easily. Especially if the flash memory is old, as you can see over here. But if you look over here, this one is 1 day retention errors, so yellow ones. If you want to retain data for 1 day or only 1 day, you still get a bit error rate over here that's quite high, which is 10 to the minus 4 over here, assuming that you've written to flash a lot. But even if you have not written to flash a lot, which is only 100 times, you still get a pretty high bit error rate over here, which is a little bit around 10 to the minus 7. So you can see that retention errors are still problematic in flash memory, especially MLC. Okay, this is just to whet your appetite, but we'll talk about some of this when we talk about flash memory. So what is the solution? Essentially, the solution is to refresh periodically. But then what is the period? You can change the period based on how old the flash cell or flash page is, meaning how many times you have written to it. Because clearly there's a relationship between how many times you have written to it and how much charge it can retain. And the reason you cannot, it becomes harder to retain charge is as you write to the cell many, many times, you wear out the cell, and this wear out essentially hurts the retention mechanisms. And we will discuss this more in flash memory. There are interesting tunneling mechanisms that happen. So basically, you refresh more often at higher program and erase cycles. And the question is, how do you refresh? So in flash memory, actually, you can have multiple different mechanisms. In DRAM, when we refresh data, we did it in place, right? You access the data, you activate a row, which brings the data to the row buffer, and then you pre-charge the array, right? That's the way to refresh. I call it kind of in-place refresh, but it's not exactly in place. You're moving the data between sense amplifiers and the row that you're refreshing. In Flash, you can do that also by programming the cells. Flash doesn't. In Flash, you need to operate things by programming. So in place means that you program the cells so that you actually compensate for the lost charge, and you add more charge to each cell that has lost charge. But you can also do something else, which is you can remap the data from one page to another page somewhere else. And this is feasible in Flash because Flash controller is an intelligent controller. It maintains a mapping table that tells you where each block is in the physical address space. This doesn't exist in DRAM. In DRAM, you get an address, and then that address is directly mapped to, directly sent to the, you get an address from the processor, and that address is directly sent to the DRAM chip. Internally, there's a mapping mechanism in the DRAM chip, but it's very limited. In Flash, you get an address from the processor, and that address is remapped completely using a logical to physical page mapping table. And then you can actually change where each logical page is located in the physical domain in the Flash memory. So this is the example of an intelligent memory controller. This enables remapping-based refresh in Flash memory. And again, if you're interested, you can read some original papers. Yes?
Is there a study on whether the number of rows in the Flash memory were out differently?
Mm-hmm. Yeah, these papers, a lot of these papers study. Yeah, there's basically spatial variation, certainly. Yes, exactly. But usually, yes, certainly there's spatial variation. Flash, not all Flash controllers try to exploit that, but it's possible to exploit that much more easily in Flash memory than in DRAM.
Because of the remapping.
Because of the remapping mechanism, exactly. If we had that remapping mechanism in DRAM, we could also exploit it, like when Girai discussed the Sverd paper, right? There's spatial variation, RowHammer vulnerability. Today, it's very hard to exploit because you need to have some sort of table to keep track of what has what kind of vulnerability, what row has what kind of vulnerability. But that's a very good observation. Okay, so this is the original paper that actually discusses how to do the refresh in Flash memory using in-place and remapping, and there's a lot of data as well. Okay, so I'm not going to go through this in detail, but there's actually more detailed characterization on different mechanisms that we have proposed to do data retention. Some of these are actually recovery. So even if you get errors in Flash memory, meaning somehow you pushed your Flash memory for too long and eventually you got some errors, you can still recover data by doing post-processing. You take off your disk and post-process it in a probabilistic manner, and you can still recover a lot of data. This is actually very interesting in storage. How do you recover data? It could be used for good or bad purposes. That's why don't lose your Flash memory. Okay. Okay, so if you want to fetch things, this is the paper that I would recommend to read. It's a long paper that summarizes a lot of the research. It doesn't cover everything we have done, but it covers a lot of the state of the art in industry and academia at the time it was written. And a lot of things are still employed in the field. Okay, there's a more up-to-date version also. Okay, we're going to get to Flash memory later on in this course. Okay, so I think to conclude, we've discussed like the radar idea early on, right? I think radar idea is a good idea, but one can come up with many good ideas, in my opinion, assuming you have the right mindset and right preparation. It's preparation and mindset and a little bit of luck. But then good ideas may be difficult to implement, right? The key is really finding the good ideas. I think that's a good step. But after that point, making them work is actually an even harder step potentially, depending on the idea. So we've kind of seen the story of how to make variable rate refresh work as much as we can, right? And that concludes the data retention lecture. I'm happy to take more questions if you have more. Otherwise, we're going to switch gears to memory latency. No, okay, it's still too early to take a break. So we're going to switch. Let's see how we switch. Okay. There's a desktop. Okay. Okay, I assume this is the, okay, 8B. Cool. Oh, okay, screen share, I forgot that. That's what happens. Better? I don't want this display thing. Okay. Looks good, okay. Okay. So the last part of this lecture was actually really about the latency impact of refresh, right? We talked about parallelizing refreshes and accesses. And in that case, we're not saving energy. We're really, well, you could be saving energy by reducing execution time, right? But we're not directly saving energy by eliminating refreshes. In that sense, like variable rate refresh is very nice because it eliminates refreshes, which is good for energy as well as performance. But the refresh access parallelization mechanism we talked about doesn't eliminate refreshes, but it does eliminate the performance overhead of refreshes or tolerate the performance overhead of refreshes. So in a sense, it tolerates the latency. So now we're going to talk about more direct mechanisms to reduce latency, which will be applicable to both refreshes and accesses. And I think this is a very important area as we discussed. So I'm going to motivate this a little bit. So we talked about robustness. We talked about energy efficiency, which we're going to get to. Now we're talking about low latency. And later in the lectures, we're going to talk about these different directions as well. So stay tuned. Now we're over here. I'm not going to cover the predictability part because that's a separate thing, right? Latency and predictability are two different things. And the way I like describing it is I'm waiting for my train, and I'm hoping that according to the schedule, it comes at 13:55, 15 minutes from now. If it's low latency and it comes at 13:53, that's not good, right? I don't want that. In that case, I don't want low latency because I'll miss it. And this happened to me multiple times in Zurich. The train was supposed to come at a particular time, but it came 1 minute early and I missed it. You know, so this is where you want predictability. I don't care about low latency in that particular case. So that's the difference basically. But in many cases, you want low latency and on top of that predictability. So it's good to keep this in mind. But now we're going to focus on low latency. So why do we want low latency? As I said earlier, I think latency is cause of a lot of the problems in our computing systems, and we don't probably pay enough attention to it. And low latency is needed to solve problems, right? Clearly, a lot of problems demand high performance, and a lot of them are bottlenecked by latency in the end. I'm just flashing these without making an obvious connection to latency, but you can imagine. But I'm going to use some analogy, which I have not used in this year's incarnation of the lectures, because I wanted to combine everything together. There's something weird in this slide. Okay, but anyway, I think that a theory of human motivation is kind of double, or is are my eyes playing some? Does it look weird? Okay, okay, anyway, we'll try to fix that. But this is, how many people know about this hierarchy? Maslow's hierarchy. Okay, that's good, that's good. Yeah, it's a famous one because it's not just about psychology. It's really about used in many domains. But this person, American psychologist Maslow, came up with this. And he basically says, if you want to, basically the first things you need to really care about is safety and security and food, etc. And if you don't have that, then you cannot think about anything else. I think humans need to be better at this in understanding that this is the case for everyone in the world these days. Unfortunately, we don't have that sort of empathy in the world, but this needs to be applied everywhere, I think. But we're applying it to the computing domain. Maybe you argue that you start with energy, right? What is energy? It's food for the computer, right? If the computer needs to run, you need energy. Is that the most important thing? I don't know. Maybe robustness? Which one is more important? Which one do you care about more, robust computing or energy efficient computing? If you don't have energy, maybe you don't care about robustness, right? It's not even running. But then maybe low latency is enough. Maybe you don't have enough energy or enough robustness, but you have enough latency. You're so quick at fixing things, then you may actually be better. Okay, anyway, this is where the analogy kind of ends. You should think about this a little bit. I think maybe if you are very speedy in correcting things, or maybe speedy in generating energy, who knows, right? Yeah, okay. Basically, latency is important. I'm not taking sides on which one's more important, but we really need everything optimized, right? As we discussed earlier, energy, robustness, and latency. So we're going to talk about latency now. But if you're interested in this, there's actually a very nice talk by my former colleague Satya, who's a professor at CMU, who works on both distributed computing and edge computing, and he's done a lot of great work in this area. I'd recommend that you watch this talk, where he really talks about the importance of latency as well as other things when you actually do edge type of computation. basically, if you want to be highly responsive, you have to actually have optimized for latency. And there's one slide that I borrow over here from him that basically says that if you actually want to interact with humans, like if you want to, let's say, enable a real world over here, this is the cognition of human mind, let's say. You need to be faster than these speeds. And he basically argues that if you actually need to beat these speeds, because you need to add value, right? If a human does something, and if you actually do this, give the same experience to that human with computing in virtual reality, for example, that's not interesting probably. You probably want to have better experience, right? If I actually go out in virtual reality, and I would like to really understand many things about my environment that I cannot do today. If I have the same experience, I'm not going to buy anything related to your virtual reality environment. So I need to be actually more superhuman in that sense if you want to enhance the experience. And that requires really low latencies because human cognition is actually very fast. Even though it looks slow, it's still very fast, right? And then there are other reasons for latency, of course, but these are his reasons over here. So I think certainly latency is important in critical situations where you need to analyze a genome, for example, and you need to make decisions in terms of, for example, if you have a critically ill patient, then you need to really understand what kind of drug or what kind of what kind of drug you need to deliver that's personalized to that person, right? You cannot wait days and days to do the genome analysis in this case. You actually need to do it right away. And you cannot make a mistake. So both latency and accuracy are important. So we're going to talk a lot about genome analysis later in some other lecture, but just to fetch things, if you want to do this in a real-time setting, latency is really critical. And we have seen that in our work also. Okay, so if you talk about data-centric architectures, this is one slide that where I try to summarize the properties of a data-centric architecture. If data is really important, which we discussed, you want to process data where it resides, which is what we discussed earlier, but you also want to enable low latency and low energy access to data. Right? Processing data where it resides reduces the access latency to data compared to a processor-centric system. But if the data is still long latency to access, that's a problem. Basically, that's why these two are actually important to do together, in my opinion. But independently of where you process the data, latency and energy to access the data is important, I think. So we're going to see that. So a lot of the studies that I'm going to show you are not going to be in the context of memory-centric computing. A lot of them are going to be in the processor-centric computing. And even then, we really need to reduce access latency. Okay, I'm not going to cover these two, but we'll talk about that later on. So I should also mention that here, I say energy. It's not just latency, it's also energy. But these are also interesting things that could be synergistic with each other. Sometimes when you reduce latency, you also reduce energy because you reduce the amount of time the circuits are active. And active circuits are very bad for energy in general. So fundamentally, reducing the latency is good for energy as well. So keep that in mind in general. That's not always the case because depending on the latency reduction technique, you may add more complexity to the system, which may actually increase energy. But well, increase depending on the trade-off. Part of it will be increased, part of it will decrease the energy. But it's important to aim for both in general. Okay, any questions? Now, let's take a look at some fundamental trade-offs. You've seen some of these slides, so I'm going to go through these relatively quickly. In an earlier lecture, in the first lecture, actually, I showed you this graph, which shows essentially how DDR memory capacity, bandwidth, and latency have improved. And we've discussed some of the reasons for it. Clearly, capacity has been the focus in memory. Latency has not been as much the focus. And if you look at some specific latencies that we're going to cover today, activate pre-charge restoration, some of them have been increasing, actually. And in fact, that Samsung and Intel paper that I mentioned say that write latencies are going to increase. So we need to somehow figure out how to tolerate them. And the write latencies are going to increase because they cannot push enough current through the access transistor very quickly. So there are circuit level reasons why these things increase. Okay, and this is the other graph that we showed. It's a longer term study, which I would recommend everyone to do if you're interested in an area. It's always good to investigate what has happened in that area. This is done by my PhD student, Manesh Patel. And you can see that over the course of 54 years or so, the capacity has increased essentially exponentially. In the recent years, maybe we're having some struggle comparatively, let's say. But still, it's a 1,000,000x capacity improvement in a DRAM chip, which is fascinating, which is essentially a similar thing to Moore's law, right? You can pack more transistors and pack more capacitors in a given area with better technology scaling. Unfortunately, latencies look very different. Overall, in the 54 years, these are based on datasheet information, you get 8x latency improvements. But if you look at the more recent past, the last 24 years, the latencies seem almost constant, right? Does that make sense? Well, it doesn't have to make sense because it's real data. You can argue with the data. The only way you can make sure that this doesn't make sense is showing that the data is incorrect. It's very hard to argue with real data. Okay, but this is the state basically. This is the state we're in. I should probably change that because today we're in the misinformation age. People don't care about data in general, right? But we're scientists over here, and we're at a university, we're in an academic institution. We should not be part of that misinformation. I had to add that, sorry, because I think there's a very big danger that we're facing in the whole world. Okay, but basically, if you look over here, this is the state. And as we discussed, this is partly a conscious choice, but partly also a conscious choice in the sense that everybody wants capacity, and that's the major design goal in DRAM chips. But partly it's because it's the harder thing to do. Reducing latency is really harder than improving capacity, because technology scaling is not on your side in general. When you go from a bigger technology node to smaller technology node, latencies do not magically reduce, especially the interconnect latencies. Okay, so if you're interested in this and other things, we discussed, for example, the relationship between memory controller and DRAM, and how the DRAM should expose more to the memory controller so that we can actually get better reliability and better characteristics. This paper actually puts a nice argument for why that should be the case, with a lot of case studies and with a lot of interesting data. I'd recommend people to look at it, and maybe we can include in a future homework too, as a potential with a potential paper to review. Okay, so I've already said this also in in earlier lectures, but there are also a lot of works. These are some papers, a select set of papers that show that DRAM latency is important for performance in many workloads. In many workloads, latency is important. In many workloads, bandwidth is important. In many workloads, capacity is important. So there are also different parts of the workload that are affected differently by these different metrics. Sometimes you actually have a really critical latency requirement. You actually have a database transaction. You want that to go through right away, right? Sometimes you have a bandwidth requirement because you have actually lots of these transactions potentially, right? And you have capacity requirements usually all the time, especially with large data. So workloads are actually a complex mix of, it's very hard to say this workload is completely latency bound, especially if you have a complex workload, because it's really a combination of these different characteristics. You can be bound by multiple things. Okay, but basically long memory latency is a performance bottleneck. So we studied a lot of workloads in this particular work, where we were trying to understand the effect of different characteristics, different DRAMs on different type of workloads. I'm going to quickly mention this. But this is a nice study that we have done. Basically, what did we try to do? Essentially, there were a lot of different types of DRAM that people were developing. And today, actually, we have a lot of DRAM. We have HBM, we have LPDDR, we have graphics DDR, we have regular DDR. If you want to learn more about those, this paper actually does a very nice job explaining what are the differences between those. I'm not going to do that because I think they're important, but they're not as fundamental, right? High bandwidth memory gives you high bandwidth memory, but we're going to talk about it at that level. If you're interested in more detail, you can look at the paper. But basically, there are a very diverse set of applications that we execute, and it's very hard to take a one-size-fits-all approach. Some applications really want more bandwidth sometimes, and this is why high bandwidth memory was developed. And clearly, high bandwidth memory is having a lot of success today because it's coupled with GPUs that can execute machine learning workloads. So the question we asked in this work was, which DRAM type works best with which application, at least on average, right? We did not look at hybrid memory. That's another exploration that we will talk about later on in this course. How do you combine different memory technologies, and how do you take advantage of these different memory technologies to improve an application or the system in general? Here, we're talking about one type of memory, and how does it work with different types of applications? And we wrote this paper and we submitted it to a conference, and I'll talk about some stories also. Basically, the reviewers came back and said that, oh, you did a very extensive study, that's great. You studied 9 different types of DRAM, etc. Why didn't you do it on a real system? Now, that's an interesting question. Like, how do you study a given application with 9 different types of memory in a real system? We discussed it in the past, right? Actually, somebody yesterday asked the question, why is the memory controller on chip, or is the memory controller on the processor chip? Because the memory controller is on the processor chip, there's no way you can change the type of DRAM that you add to the processor chip, because that processor chip has a memory controller that can communicate with a specific type of DRAM. It could be DDR, it could be HBM, it could be LPDDR, but you don't have a processor chip where you have, I'm not going to say 2, but 3, let's say 3 of those, let alone 9. So you can see that sometimes reviewers just pull things out of their hat and they say things. That's why you need to believe in the work, and you need to really understand what you're doing. And you don't trust the reviewer to really understand what you're doing. Okay, basically this study cannot be done on a real system, because there is no real system that can support so many memory controllers. This will become even more clear when we talk about memory controllers, because each memory type requires a lot of pins. And if you really want to add 9 different types of memory controllers, and if you want to support all of them, you really need to have hundreds of additional pins in your processor chip. And that makes no sense, because and first of all, there are multiple reasons why it doesn't make sense. One is it's expensive, clearly. And then what are you going to do with it, right? That's another question. Why would you design a chip that can communicate with 9 different types of memory, with 9 different types of memory controllers? Okay. Now, this problem is alleviated if the memory controller was not on chip, was not on the processor chip. If you had another chip that is actually separate, then you could actually plug and play different types of memory by changing what kind of chip that you communicate with, right? But we'll have more stories about this in memory controllers. Okay, so in the end, we studied a bunch of applications and workloads, and we looked at 9 DRAM types. So I was right in 9, as you can see. Not all of them exist today, but essentially, I'll go through this relatively quickly. These are DDR3, DDR4. Today we have DDR5. At the time we didn't have it. This is graphics DDR. You can see that they have different characteristics. They have different upsides and downsides. For example, going from DDR3 to DDR4, actually latency is increased. And we wanted to understand whether this is good or bad for many workloads. GDDR4 increases area and power. And we wanted to understand the effect of that on energy. And then there's high bandwidth memory. At the time, we had hybrid memory cube, which doesn't exist today for various reasons. Power was one of the issues, actually. But I mean, HBM and hybrid memory cube, in my opinion, are relatively similar. They're both 3D stack types. Its interfaces are a little bit different. But essentially, we studied that. These are 3D stacked DRAMs, at least in the ideal incarnation, they can be 3D stacked, which HBM right now is stacked in a 2.5D manner using interposers between a memory controller and the HBM, but there's no reason why the memory controller cannot be in a dedicated logic layer. In fact, in HBM4, this is going to happen, I believe. Okay, but essentially, they have different kind of characteristics. For example, hybrid memory cube made the choice of having narrower rows and higher latency. And then there were some other low power technologies. Some of these are high bandwidth, low power, wide I/O, which I'm not sure anybody uses these days. Does anybody use wide I/O anymore? Maybe not. I think HBM kind of overtook a lot of these things because, yeah. These are lower power, high bandwidth technologies that kind of didn't survive, let's say. But LPDDR survives. These are low power, not so high bandwidth technologies, but they're low power. So there's a benefit over here. Okay. Without going into a lot of detail, basically, there's a lot of analysis in the paper that I'm not going to talk about over here. You can read the paper for more detail, but I'm going to point out one thing that we found. Essentially, new DRAM types often increase access latency in order to provide more banks, higher throughput. Essentially, they make the trade-off to get higher throughput, you have higher latency. And we wanted to understand this trade-off. Is that a good idea in a lot of applications? And essentially, we found out that many applications do not benefit from that trade-off. For example, a lot of operating system routines, file I/O, process forking, they actually lose performance when you go from DDR4 to HMC, for example, DDR3 to HMC. There are also other applications that lose performance when you go from DDR3 to DDR4. Even though it's a slight performance loss, they essentially do not gain benefit from going from one memory technology to another memory technology, right? Ideally, you would get benefits. If you don't get benefit, why do you go from one memory technology to another technology? If this curve should not be flat, basically. This curve probably should not go down also, as you can see, but it should not be flat either. So it's good to think about this, basically. So what benefits and what doesn't benefit? Okay, so these are some conclusions that we draw in the paper. essentially DRAM latency is still a critical bottleneck for many applications. And additional parallelism that are provided by some of these new technologies, like high bandwidth, is not really fully utilized by a variety of the applications. And if you want to utilize them, you need to change your application somehow, meaning you need to exploit the spatial locality. So some of the technologies that reduce the spatial locality, meaning the row buffer size, actually hurt the performance of many applications because the applications have spatial locality and they cannot exploit that. But if you actually want to exploit also larger parallelism, you need to actually change the application. Okay, and also we found out, which was also found out earlier, but we also kind of replicated this finding that low power memory can provide significant energy savings without sacrificing significant performance. And I think it's good to think about that going into the future. Can we actually reduce latency as well as power at the same time? Okay. So I'm going to skip this because we already talked about this. But essentially, you can find more information in the full paper. We also actually released a lot of tools related to it. This was used by industry and academia. But you can also, if you're interested in this sort of study, I think this sort of study is important to do, especially with modern set of applications. The study was published in 2019 after being rejected a couple of times. So you can see that the research was done actually even earlier. But it's good to revisit what's happening in the DRAM as well as storage space for emerging and new applications also, because clearly the application landscape has also changed, given that we're in 2024 right now. Okay, but basically the conclusion is, even though there are new DRAM types are coming, some of them actually increase latency, and this actually hurts performance. Maybe this is a good time to take a break. I have a nice clean cut over here. So I'm going to motivate a little bit more the memory latency problem. Hopefully this motivation was enough, but I think I'm going to also give you my personal story because I actually worked on memory latency for a really long time. My PhD thesis was all about tolerating memory latency from processor-centric systems. Even my first works before my PhD thesis was about prefetching. How do you tolerate latency that's visible to the processor? So I'm going to give you that story first, and then we're going to jump into how to actually fundamentally reduce latency as opposed to tolerating the latency. Because tolerance is, I think, it's nice, but it has a limited, like, let's say, how should I say it? It's important, it's fundamental, it's nice, but unfortunately, it's not really solving the real problem. The real problem is the fact that you have high latency to begin with. You can do all sorts of things to tolerate it, and that all adds complexity. If you don't solve the latency at the heart of the problem, then I think you're going to keep solving the toleration of the latency, and you're going to make your systems more and more complex. And this is, I'm going to give this to you because I think this is my personal story and personal belief based on what I have done over, let's say, 25 years or so in computer architecture. And so I think it's fascinating. This doesn't mean that those tolerance techniques are not important. Don't get me wrong. I think we'll see that also. Okay, so now let's take a break. Oh, is there a question? Okay, let's take it before we take a break, given that we're going to go to the second part of the lecture. Okay, sorry, you couldn't read it?
I can read it also, but I need a microphone.
Okay, you need a microphone. Okay, basically, this person says, with NAND SSD speed scaling much faster, will we have an edge system that omit DDR memory totally and solely rely on the NAND SSD, considering the fact they don't wear out much faster? I don't know the last part, but solely relying on NAND SSD. Basically, I think the difficulty is if you want to get rid of the main memory, now you're increasing the latency a lot to the SSD. So I think it's going to be not so easy to get rid of main memory, especially in a high performance system. If your goal is to actually have a low power system, yes, but reducing the latency of NAND to the level of DRAM today, I think is very difficult. I think it's good to research the reduced latency NAND, but bridging the latency gap between NAND, flash, and DRAM is very, very tough proposition. It's very hard to see that happening anytime soon, in my opinion. That's why DRAM is a very nice technology that has its own place, right? That's why we have this memory hierarchy today. But of course, if you start doing in-storage processing or in-memory processing, now that changes the game, in a sense, right? But still, the latency is to access flash, as we will see in later parts of the course. Maybe Mohammed will talk about that because he's done a lot of research along with us. Essentially, it's very hard to reduce the latency to flash to the levels of DRAM. So if you want to do in-storage computation, we will also see that you actually may want to take advantage of the DRAM that's inside the storage system, because there's DRAM in the storage system. Okay. No more questions? Okay, let's take a break until 14:19 then, and then we'll continue with the memory latency problem. maybe. No. Okay. I think it's time to get started. Am I correct? 219? Okay, I thought I said 19, but yeah. Predictable performance, you know. Okay, let's get started. Any questions before we move on? Anything that came to your mind? Okay, otherwise, clearly high memory latency is a significant limiter of performance and energy efficiency. And this is becoming increasingly so with higher memory contention, which we will discuss in a later lecture in multi-core and heterogeneous architectures. This exacerbates the bandwidth needs, exacerbates the quality of service problem. Basically, higher latencies are bad for quality of service, predictability, and also bandwidth, as we will see later on. Because if you want to tolerate the higher latency with more parallelism, more prefetching, more waste, then you need more bandwidth. And also it increases processor design complexity because you have a lot of mechanisms to tolerate memory latency. This is a slide that I used first from my PhD proposal and also in my PhD defense. Essentially, these are conventional processor-centric latency tolerance techniques. And you know a lot of these, and we're going to cover some more of these later on. But caching, for example, it's widely used. Unfortunately, it doesn't work all the time. Although this is what people do, right? They keep adding caches and caches and caches and caches and caches. Locality is strong, but there's a lot of inefficiency in those caches. There are a lot of studies that show that more than 80%, 90% of the data that's stored in caches is useless. Basically, you can replace it without having any impact on performance, but you brought it over there. So there's a lot of waste in caching. Prefetching, these are all ideas that were developed in the 1960s, as you can see. They've been refined over many years. But prefetching is also a nice idea. And I think we should work more and more on prefetching because it's an area that's not been worked as much as caching has been worked on. But unfortunately, we don't have the best prefetching mechanisms. And these are processor-centric again, right? It reduces the latency from the perspective of the processor. Caches also reduce the latency from the perspective of the processor. Multi-threading tolerates latency if you actually have one long latency access happening in one thread. Why not have other long latency accesses parallelized in other threads, right? This actually tolerates the accesses, latencies, and this is actually a very well-known topic. It was initially employed in CDC 6600, which is a nice processor. If you don't know about it, there's a beautiful book by Jim Thornton about this one. But essentially, this is also wasteful in a sense, right? It requires more bandwidth. This is one of the reasons why we need more bandwidth. Because there's heavy levels of multi-threading employed by some architectures like GPUs, for example. Also like machine learning accelerators, not just GPUs. And also there's another issue over here. If you want to improve single thread performance with multi-threading, that's a tough call. A lot of people have tried that and it's not very easy. And then there's out-of-order execution, which is essentially executing instructions out of order such that if one instruction cannot proceed because it has a long latency memory access, hopefully some other instructions can be executed. And now you tolerate the latency of that long latency memory access with those other instructions executions. But unfortunately, this also requires extensive hardware resources, especially if you want to tolerate very long latencies. So basically, none of these really fundamentally reduce latency. This doesn't mean that they're not important. They're employed actually in our existing systems, and they're actually refined a lot, including caching. But they don't really reduce latency. Yes?
So I was wondering, like in time-based research, is there any progress anymore on caching and prefetching?
Yeah, certainly there's progress, and we're going to discuss some of that in later lectures. We hope to have a lecture on prefetching specifically, and we'll probably cover caching. But I mean, there's certainly progress in all of these areas. Probably prefetching has the most potential from my perspective, and there's a lot of work. Like we're doing a lot of machine learning-based prefetching also to do things better. There's also machine learning-based caching mechanisms, but we're going to get to that later on in the processor-centric part of the course, maybe. Okay. But I'm going to give you one idea. As I said, I want to give you a little bit of what I think about it and what I have worked on. This is my PhD thesis. It's run-ahead execution. And I really like this idea. And I'd recommend people to work on their PhD thesis on ideas that they are going to like after 20 years or so. It'd be nice. But basically, ideally, we want perfect caches. Basically, everything hits in the caches, and you keep computing. You never stall for any access, right? This is what we really want. Prefetching tries to get there, but it's not easy to do that. So if you have a out of order execution with a small instruction window, you basically get a cache miss because you just get cache misses. And then computation continues until your instruction buffering becomes full. After that point, the processor stalls. And then after the miss gets serviced and the processor can continue and until it gets to the second long latency miss. So this is very common. This sort of timeline is very common in many applications today. That's why in earlier lectures, when we looked at data from Google, for example, most of the time the processor is waiting because this is real. This happens. Now, the idea that we have developed, we called it run-ahead execution, is a simple idea. When you get to the load miss, after some point, this load miss becomes the oldest instruction in the window. But you cannot finish it because you didn't finish the load. You didn't execute it because you're waiting for data from memory. Instead, checkpoint the architectural state, meaning take a checkpoint so that you can go back to that point and start speculatively executing instructions. And hopefully that speculative execution will lead to some cache misses that you could not have discovered by stalling. Clearly, you're not executing anything while you're stalling, right? But while you're in this run-ahead mode, you're in a speculative processing mode where you're not waiting for cache misses, but you keep executing instructions. And if what happens to the value of the cache miss that you did not wait for, you basically mark it some way, right? You mark it invalid, or you put a value, you predict the value. This is purely speculative execution, and you're really executing on the program path. And this leads to another cache miss that you can generate, and you can start that access of that cache miss. And this could be parallelized with the first miss. After some point, the first miss returns back from memory. You flush the pipeline, restore the checkpoint so that you go back and re-execute load one, re-execute from load one, and load one hits. And when you actually get to load two in the real execution instruction stream, this load two also hits because you've actually prefetched it in the speculative mode as opposed to waiting for a long latency cache miss. And then you save cycles. Sounds good, right? Of course, there are a lot of things that you need to do to make this really work nice, but this basic idea works and has been implemented on multiple processors. We're going to cover this sort of prefetching mechanism later on. And for example, it was on Sun Rock. This is data from Sun when it used to design processors. They became Oracle afterwards. They got bought by Oracle. But you can see that if you do run-ahead, that's their name for run-ahead, Scout. Essentially, it's a Scout thread from their perspective, since everybody needs to rename something from there for commercial reasons. They had to rename it to Scout, which is not a terrible name, actually. They could have done much worse job. But basically, if your processor, these are commercial workloads that they were interested in executing, and you can get 40% better performance, which is actually very much in line with what we have reported in our papers. Or you could basically add run-ahead on top of a cache and you get better performance. Or you could just do a run-ahead and save the amount of caching that you add to the processor. Basically, if you want to have this performance level, you can either get it with run-ahead with 1 megabyte cache or no run-ahead with 8 megabyte cache. That sounds good, right? So these are interesting trade-offs that enables. And run-ahead is much less costly than 8 megabytes of cache or 7 megabytes of extra cache. Okay, so if you're interested, there's the paper, and we're going to cover some of this later on when we talk about prefetching. And there's a lot more work to make it improved and better. And we have actually, this is an earlier incarnation of the course. You can see that's 4 years ago, but we'll have more prefetching lectures. And this paper was given a Test of Time award, so we're very happy about that because it influenced industry and it influenced the thinking also. So we will discuss that later on. But now I'm going to deconstruct it. Even if you add run-ahead execution over here as a latency tolerance technique, that also doesn't fundamentally reduce latency, right? I gave you one mechanism, another mechanism over here that really tolerates the latency. So now we're going to talk about how do we fundamentally reduce latency. And I think this is really necessary because you cannot keep tolerating latency and keep increasing the latencies because it's, in the end, there's no end to this, right? We should really start a point, again, if we talked about thinking like a 10-year-old, like you give it to a 10-year-old, 10-year-old would say maybe start with a low latency system and then optimize it, right? That's what we want to try to do really. So basically, where is the inefficiency coming from? Where is the overhead and latency coming from? I think there are at least two reasons. There could be more, but we're going to cover at least two reasons. One is Modern memory is not designed for low latency, especially DRAM, large memory. I'm not talking about small memories like SRAM. They are somewhat designed for low latency, but they're also small. And once they become larger, they also become longer latency, but still, because they're expensive, costly in terms of how many bits how much area you need to store one bit, they're still lower latency, right? So they're too expensive, basically. We want large capacity and low latency at the same time. So essentially, modern DRAM is not designed for low latency. The main focus is cost per bit capacity, as we have seen. And the second source of inefficiency, so basically the first, if you want to solve the first one, we need to rethink the DRAM microarchitecture, perhaps. The second one is maybe easier to handle. Basically, even though you don't design DRAM for low latency, you determine some latency parameter, and that latency parameter is worst case, based on worst case condition and worst case devices to maximize yield in DRAM chips. Maybe that's not the right thing to do. Basically, much of memory latency is actually unnecessary if you take this into account. And we're going to show that also with real DRAM chips. So basically, the goal is to reduce memory latency at the source of the problem. And all of these ideas are applicable to actually SSDs, other large capacity memories as well. But we're going to look at it from the perspective of DRAM. So how do you truly reduce a memory latency? So these are the two reasons that I already showed you. And we're going to look at how to reduce it. So we're going to tackle the reason one first. How do you design the DRAM microarchitecture for lower latency? So as opposed to maximizing capacity per area, we're going to put latency as a consideration also. Maybe we will have a little bit more area, but much lower latency, hopefully. So it's good to explore this spectrum or continuum of design between latency and capacity, right? And then we're going to tackle the one-size-fits-all approach to latency specification. Today, basically, we use same latency parameters for all temperatures, DRAM chips, parts of a DRAM chip, all different voltage levels, and also application data. We're not going to talk about the application. Well, we're actually going to talk about the application data also. You can actually do something over there as well. For example, if an application can tolerate some errors, you can reduce the latency to match the error rate that the application can tolerate in that part of the data. And this is we're going to exploit all of these basically. Does that sound good? Hopefully that's interesting. And as I said, these are fundamental. There's nothing that makes these only applicable to DRAM. There are works that have applied to these to SSDs. Also, emerging memory technologies like phase change memory and STT-MRAM. There are other works that I'm not going to cover, which are still interesting. Okay, let's look at the DRAM microarchitecture. But before we go into it, let me give a brief overview of inside a DRAM chip. We kind of talked about this, but I want to give you a ground-up view. Essentially, if you look at a DRAM module, each chip looks kind of like this, right? This is the die photo of a chip. And there are many goals in the design of a chip, and usually cost and density are the top goals, and latency comes at the bottom, let's say, even with low latency DRAM. So people have actually produced low latency DRAM, which we're going to talk about, but they're not a major part of the market, as you can see today. And they're very expensive today. You can buy perhaps some of those, but not so easy. Some of these low latency DRAMs are used in routers, for example, very fast, that they need to do very fast routing. Okay, so this is a DRAM chip. You can see a bank over here, and this is kind of a cartoonish overlay. Clearly, a bank has many more subarrays than two, but we're going to look at some of these subarrays. And you know how a sense amplifier operates by now. It's a cross-coupled inverter. And there's an enable signal over here. Once you enable the sense amplifier, this is the logical 1 state. The bit line, the top is 1, VDD. The bottom is 0, the opposite. And this is a logical 0 state. There are two stable states, basically. And what the sense amplifier does, as we have discussed in the past, is when you enable it, it checks whether the voltage level above is larger than the voltage level below. And when you enable it, if that's the case, then the voltage level at the top is driven to VDD, and the voltage level at the bottom is driven to 0. That's the sensing process, essentially. We can go into more lower level, but there's no need right now. Okay, and this is the capacitor we've seen. This is the empty state, and this is the fully charged state. These are the ideal states, of course. One is logical 0, one is logical 1, as you can see. And capacitor itself is small, so it cannot drive circuits. And reading the capacitor destroys its state. That's why you need to couple it with a sense amplifier to be able to read it. So this is what we want, actually. When you see this capacitor, I mean, you couple it with a sense amplifier, you want to get 0 over here. When you see this charge level and you couple it with a sense amplifier, you want to get VDD over here. So this is how things are connected, as you know already. Essentially, you have an access transistor, And initially, the bit line and bit line, the other side of the bit line are at a reference voltage. This is the pre-charge state, 1/1 VDD. And when you connect the capacitor to the bit line through the access transistor, the capacitor charge perturbs the voltage over here. And that perturbation, that small perturbation, gets sensed when the sense amplifier gets enabled. And the sense amplifier drives the top to VDD, top part of the bit line to VDD, and the other side to 0. Makes sense, right? We've kind of seen all of this, but this is just to make sure everyone's on the same page. And then, in turn, this charge level over here that is driven to VDD gets restored into the capacitor. That's the restoration process called charge restoration. And that's how you ensure the destructive read is overcome, right? Whenever you read the capacitor, you destroy the value, but then after sensing, you restore the charge so that the value destruction is gone. Okay, so now you can actually build larger blocks. A DRAM subarray consists of many of these. Essentially, this is one single bit line, but you add essentially a lot of cells to the same sense amplifier. Only one of them can be enabled, maybe, but multiple of them can be enabled, as we discussed in the memory-centric computing lectures, and as Ismail will tell you maybe in a future lecture. He's trying to enable even more. Okay, but in existing operation, essentially, this is what a subarray looks like. This is a 4 by something, 6 by 4 subarray, right? 24-bit. Yeah, and then these are the sense amplifiers. And there's an enable signal for the sense amplifier. Then these are the word lines, essentially. So there's a row decoder to decide which word line should be activated when you get a row address. Okay, and this could be of the size 8 kilobits, for example. It could be, it's dependent on the size of the row buffer, basically, and the design. And these are two different cell arrays that belong to the same subarray. And then you can have different row decoders, or at least local row decoders for the same for the same subarray. There's one local row decoder for each subarray, and then there are different row decoders for different subarrays. And imagine you can have 128, 256 of these. There of course needs to be another decoder over here that decides which subarray the access should be routed to. So it's a hierarchical decoder, basically. Okay, and then there's circuitry that takes a small chunk, like a column, of the data that's being read from a subarray and sends it out to the DRAM chip. That's called bank I/O. We're not going to talk a lot about that, but you can read papers on that topic. So the address gets routed, and then there's also, this is the row address goes to the row decoders, and the column address goes to the column decoders over here, and then eventually you get the data. Okay, so the memory channel is actually smaller. You aggregate many bits from different chips to get 64 bits, for example. And then there's internal prefetching that goes on in a DRAM chip that I'm not going to talk about right now. Those are a lot of interesting things that's happening inside the DRAM chip also. Okay, but this is what the memory chip looks like. Assuming the memory channel is 8 bits, you get 8 bits with a given access. And there's a shared internal bus, which we kind of saw in prior works like row clone, for example. We took advantage of that shared internal bus, right? Okay, so how does DRAM operate? Again, this is going to be a review very quickly. We activate the row. That's part of the latency, right? So you need to supply the row address, drive the word line, and the bit lines get connected to the cells, and all of them get sensed, and the data gets latched into the sense amplifiers, cross-coupled inverters. That's the activation process. Oop. And then if you're targeting one column, you read or write from that column, which essentially you need to supply the column address, and that column gets transferred through global bit lines to the bank I/O circuitry and then out of the DRAM chip. Okay, so there's also read-write latencies, as you can see clearly. And then if you want to activate some other row, either in the same subarray or a different subarray or in the same bank, you need to pre-charge the bit lines or pre-charge the bank, which essentially brings the state back to 1.5 VDD on the bit lines, right? And that takes time also. So you can see that these are the 3 major time takers, if you will, when you do a DRAM access. You can target all of these. You can target reducing the latency of every single one of them, and we're going to target all of them, right? Does that sound good? Yes?
So when you pre-charge, do you have to pre-charge like the local bit line in the subarray that you targeted? Right?
That's correct, yes. Yes. Okay. So if you want to learn more about DRAM, there's actually a nice section that we wrote with my prior PhD student, Vivek Seshadri, who did a lot of the works, row clone, Ambit, etc. Yes?
So the individual row buffers, the local row buffers within the subarray, how are they connected to the bank card?
Well, they're global bit lines that are not shown over here. Yes.
Global row buffer.
Yeah, we called it global row buffer in our earlier papers, but I tried to refrain from that terminology because it's not really a row buffer. It's much smaller. So basically, the issue is you have local bit lines. You have 8 kilobytes of data, let's say, right? And you have very short bit lines, and you can put many of them together, right? But if you want to take out a small piece of it, or if you want to take out all of them out, it's very hard to drive very thin wires. So global bit lines need to be wide. So fundamentally, you can take out only a small portion from the local row buffer, right? So those global bit lines are thick, and they require a lot more power, so there are fewer of them. Hopefully that makes sense. In some of the papers, you will see that. But yes, in earlier papers, we use some global row buffer terminology, which is a bit confusing. It should really be global I/O. Do you agree? Okay, because you're looking like the. Okay, let's discuss. So, okay, a better one. Maybe, okay. It's good to critically think about this also, right? The goal is not to just think this is the case, but the question is, can you do better, right? It's always good to do that. Lauterbach designed sector DRAM, so he's going to come up with a much better DRAM soon. Even before sector DRAM is presented. Okay, so now I've given you the basics. Let's take a look at how the DRAM microarchitecture is designed. And I'm going to give you some ideas. I'm going to give you one of the earliest ideas that we have developed here at Latency DRAM. But basically, the question is, what causes the long latency? Clearly, there are a lot of stuff that's happening in DRAM. Essentially, you have the cell array I've shown you. It divides into subarrays, and then there's a I/O that connects with the outside world. So there's a subarray access latency, and then there's the I/O access latency over here. And DRAM latency is really a combination of both of them. So we argue in this work that subarray access latency is dominant because you can tolerate a lot of the I/O access latency, and there are methods where you can reduce the I/O access latency, prefetching, etc. So let's take a look at the subarray first. So why is the subarray slow? So this is another picture of the subarray over here. We have the row decoder, we have the sense amplifiers, and we have a subarray over here. This is the cell. Normally, what DRAM manufacturers do is, normally the sense amplifier needs to be large, right? Because it has a lot of circuitry to sense things. It's at least a cross-coupled inverter, but there's also other circuitry to do better sensing, better restoration, better pre-charge, etc. And this needs to be large. Whereas the cell itself can be very small, right? So what DRAM manufacturers do for cost purposes or capacity purposes, they don't want to put a lot of sense amplifiers, meaning that fundamentally they want to have a longer bit line. Let's say 512 cells or 1024 cells per bit line, right? This amortizes the sense amplifier cost across many of these cells, and it leaves a smaller or relatively smaller area. I mean, you could also put 64,000 cells, right, on the same bit line. The problem is now that interconnect becomes overly loaded and its reliability becomes not so good. So there's a sweet spot in terms of how many cells you put on the bit line. So usually that sweet spot is 512, 1024, around that basically. It could vary basically. But of course, this is not good for latency, right? If you really want low latency, you want to reduce the bit line, right? Basically, if the bit line is long, it has a lot of capacitance, and this leads to high latency and power. But if you want to get rid of that, you could actually have one sense amplifier per cell, meaning that in a single bit line, you have only one cell. Right, but that sounds terrible for cost now, right? So basically, now you can see the trade-off between latency and capacity. And this is a very fundamental trade-off. It manifests itself in essentially everywhere. There's always a trade-off between latency and capacity. Like if you want to fill this room with many people, it'll take longer. That's latency and capacity trade-off, right? Yes.
What's actually the main cost of having a longer bit line? Like, is it the time to pre-charge, for example? Or?
Basically, there's capacitance. And that capacitance affects the pre-charge time. It also affects the reading time, right? Whenever you're actually sharing charge and sensing. It affects the sensing time. It also it affects everything: sensing, restoration, as well as a pre-charge. Large capacitance is not good for latency, basically. It's the RC delay that you get. It's also not good for power, as you can see, because there's the capacitance, essentially, power is really CV square, right? That's dynamic power. And if your capacitance is larger, then you need to actually, well, dynamic power is activity factor times C, capacitance times voltage square. And if your capacitance is larger, clearly you have power. But if your bit line is also longer, you may actually need to operate at a higher voltage. So your power actually increases in a like cubic manner if you have a longer bit line and if you don't keep things under control. So you need to increase both capacitance as well as the voltage potentially. Right. Does that make sense? Okay. Okay. So this is the trade-off. Basically, there's a trade-off in terms of area versus latency. If you want to optimize for area, you want long bit lines like this. But if you want to make it faster, you chop the bit lines into smaller pieces and have smaller subarrays, let's say, shorter bit lines, but many more sense amplifiers. Okay, clearly this is more costly. So this is the trade-off. This is a nice trade-off. These are beautiful pictures from Dongkyok, who did his PhD thesis on this topic. Okay, basically this is the trade-off we have. Let's take a look at this trade-off. If you do some simulations or some estimations, maybe not necessarily simulations, this is the estimate that we have. Essentially, ideally you would like cheaper and faster. Ideally you would like to be at this operating point over here, right? And this is normalized to the commodity DRAM, which we assume makes the trade-off at 512 cells per bit line, optimized for area. Now, if you actually reduce the latency by having smaller subarrays, you can actually get reduced latency, right? Clearly, you can reduce the latency a lot, maybe even further, depending on what you do. We call this fancy DRAM. It's called short bit line. There's actually FC DRAM. That sounds like fancy DRAM. It's called fast cycling DRAM, but that's one low latency DRAM. There's also RL DRAM, reduced latency DRAM. I think that was from Micron. But essentially, you could buy these things, except they're extremely expensive because they're for two reasons. One is the area cost is much higher. And maybe we underestimated the area. I should also say that. These are also not easy to estimate all the time, but you get the idea, right? As you go from here to there, your cost is increasing a lot. There's also another reason why these things are not cheap today, because they're not commodity, meaning these are manufactured especially at a low volume. And as a result, you get more expensive DRAM. So you may actually go and buy this DRAM, but you have to pay a lot for it. That's why people who really, really want low latency today actually buy these like very fast routing network routers. Okay, so this is our goal, basically. Can we actually break this trade-off? Can we have some low latency part in a DRAM? And this is the idea. Basically, if you want to get the best of both worlds, or at least approximate the best of both worlds, sometimes you need to think about heterogeneity, because you really want two different things. You want to optimize for two different metrics, and heterogeneous designs are actually usually good for this purpose, right? So basically, long bit line leads to small area but high latency. Short bit line leads to low latency but large area. We would like small area, ideally, but we also want low latency, but there's no magic, unfortunately. So what you want to do is maybe create that low latency area. So basically, enable an area inside the DRAM subarray that gets you low latency. So that's the idea over here. Yes, it's not perfect, but maybe there's no perfect thing. And maybe the perfect thing is going to be your idea next. Next year, maybe there'll be a much better version of this. But this is the idea. And I think this is a clever idea. Essentially, you get high capacity. It's the same capacity as long bit line, but maybe a little bit cost. You get the low latency of this when you're accessing only this part. But then you need to isolate the two parts, the high capacity part from the low latency part. And to isolate them, we add isolation transistors. When you're accessing the lower part, you disable the isolation transistor so that the bit line looks small to the sense amplifier, so the capacitance is low. When you're accessing the top part, you connect the isolation transistors, and then the bit line is still long. Okay? So if you want to take advantage of this, you'd better put your data as much as possible to this area, right? Okay, so that's the idea over here. I think I've already said everything that I'm going to say. But small area using long bit line, this is a low latency when you turn off the isolation transistors. because the loading on the bit line is low, essentially, at that point, right? If you turn off. When you turn on the isolation transistors, unfortunately, latency is a bit higher, because now you have to go through the capacitance and the resistance of the isolation transistors also. So basically, this is what it looks like. This is at the time commodity DRAM. This is row cycling latency. If you this near segment reduces latency by 56%. This is a wrong bar. It should really be somewhere here. I still haven't corrected that. There's a version of this talk where I corrected it, but I cannot find that talk. But basically, you reduce the latency of near by 56%, assuming you have 32 rows in the low latency. You'll see a low latency segment or near segment. But far segment increases by 20%. This is the power. So power also reduces significantly in the near segment, but it increases when you're accessing the far segment. And area of it is significant. So it's not small, but it's not huge. It's not as large as adding more row buffers. Isolation transistors still need to be reliable, so we estimate about a 3% area overhead in DRAM. So this is how you can break the trade-off. Essentially, our goal is this. And if you can come up with an architecture that actually has all of the cells here, that's great, without having any magic. Magic is not allowed. It's very tough to break this trade-off. That's what I'm trying to get at. But basically, near segment brings us out of that Pareto curve, as you can see. But far segment puts us a little bit farther, as you can see, assuming it's still 512 cells per bit line. Okay, so now how do you take advantage of it? So we envision this as a substrate that can be leveraged by both hardware and software, or either of them. And there are many potential use cases that we have showcased in the paper. For example, you could manage the near segment as a hardware managed, memory controller managed, inclusive cache to far segment. Basically, far segment is really your main memory, and the near segment is an inclusive cache. Basically, its cache is part of your main memory, right? Or this could be exclusive cache. Basically, both of them can be part of your main memory, but then you need to swap things between them, because this is what exclusive means. Data is not replicated in the main memory and then in the cache, right? Or you could do some profile-based page mapping by the operating system. Everything is your main memory still, and the operating system decides what goes where. This is also interesting. Now the operating system needs to be aware of banks and also near segment and the far segment. I think these are very interesting ideas we were talking about yesterday, for example, not allocating pages or not refreshing pages that are not allocated, right? I think we really need to rethink that operating system architecture interface going forward. And this sort of architectures also enable some rethinking. That's one of the interfaces that are actually one of the most important interfaces that are very rigid today. Operating system and architecture, even though they could be co-designed really nicely, I believe we're doing a very terrible job in our systems. And we're going to talk about virtual memory later on, for example. Virtual memory is one example of that. What's happening? Am I not doing well?
No, we have a question.
Oh, okay, you have a question. Let me finish the slide and then you can interrupt. Interrupts are another thing that we need to deal with. But yeah, fundamentally a very single core concept. Very weird. Well, okay, I don't want to get started. But you could also simply replace DRAM with TLDRAM and test your luck. Meaning, you have DRAM today. Its properties look like essentially this. Replace it with a memory whose properties look like this, and hope that you get the benefits of the near segments. This is hard to make work because some data will be in the near segment, some data will be in the far segment. And if your really latency critical data or frequently accessed data is in the far segment, you're in trouble, right? So just simply replacing DRAM with TLDRAM didn't work in our experiments. Yes?
What fraction of rows?
We're going to talk about that. Yes, very good question. What fraction goes to near segment? What fraction goes to... basically, it's a trade-off, and we will see that. Okay. Are you going to interrupt me or no?
So the question is, can we put a sense amplifier on both ends of, I guess, the subarray and optimize the data path based on the location of the data?
I think we're going to see something like that later on. Hold on to that. Maybe you'll ask it later. But yes. Okay. It's an interesting question. Okay. Okay, so I'm going to show you some results with inclusive cache, meaning this is what we're going to look at. Essentially, you have far segment, you have near segment, and clearly you have the row buffer or sense amplifiers. Far segment is going to be our main memory, and near segment is cache. So we're going to lose capacity in main memory. That's not necessarily the best way of doing it, but we're going to see some performance improvements also. So basically the question is, how do you efficiently migrate a row between segments is one question, but you've already seen something like this, row clone, remember? So this paper kind of takes advantage of row clone-like mechanism. And the second is, how do you efficiently manage the cache? Meaning, what do you cache in the near segment? And is an area that can actually, where you can actually develop a lot of mechanisms. People have developed a lot of caching mechanisms, which we're probably not going to cover in this course. We've covered in digital design and computer architecture, some of them. But you could apply previously developed caching mechanisms, but also you could be a little bit more intelligent and recognize that this caching happens at a very large granularity, like 8 kilobytes or so, and maybe design better caching mechanisms. In this case, we didn't design better ones. We tried, but we actually look at a very simple LRU-based mechanism, and we'll see that it'll actually provide good performance. So basically, how do you do the intersegment migration? It's row clone. I'm not going to go through this again. We've kind of talked about that. You basically copy the data from the activate source row, which brings data into the sense amplifiers, and then activate the destination row in quick succession. That brings the data into the near segment, right? The source and destination needs to be in far segment and near segment if you want to do that. Okay, and this is low latency. How do you manage the cache? Basically, we do LRU, but the paper talks about some different mechanisms. Basically, least recently used the eviction mechanism from the near segment is evict the least recently used row in the near segment. Okay, I believe there are much better mechanisms, but even this one gives performance, as you can see, based on the number of workloads. I believe there are 80 workloads or so. We get significant performance improvements, about 10%. There could be more, but you run into bandwidth constraints as you actually, I guess you tolerate things better if you actually increase the channels, etc. Okay, and then this also reduces the power consumption, and that's also significant, as you can see. In fact, power consumption is even more significant, perhaps. So I think this sort of idea is very interesting because it's, again, another idea that reduces power and reduces latency at the same time, improves performance. And as I said earlier, we should be really shooting for those ideas. If this was a trade-off between performance and power, this would not be as interesting, I think. Okay, this is the answer to your question. This is some data, basically, that shows that what happens, assuming you use the same management policy, LRU, assuming the same workloads, what happens to the performance improvement that you get compared to the baseline, assuming you have, with different number of rows in the near segment. The assumption here is that the far segment, the total near segment plus far segment already has all 512, right? And clearly, as you go from 1 to 256, you get larger cache capacity, but higher cache access latency also, right? And also higher power. So the benefits actually decrease after some point, and we have the sweet spot at 32. But even 1 is actually not bad, as you can see over here. This is actually interesting because 1 gives you some ability to tolerate row buffer conflicts. So if you have a bank conflict, you don't actually incur very high latency of accessing the far segment all the time. You just actually access the near segment. So it's good to think about this. Okay. Okay, but you cannot dynamically do this as far as I know. If you can come up with a dynamic architecture, that could be interesting too. Without cost, without a lot of cost. Nisa is thinking about that now. Okay, so this is the paper. I still like this paper a lot. And then we tried to make it a little bit better, as you will see later on. Any questions? Yes. Yeah, we're going to talk about that. I think there are later papers that talk about this. We're going to basically, yes, it doesn't work very well with the open bit line. And the Lisa paper covers that, but I'm not going to cover that in detail. I'm going to cover something else that I think answers your question in a little bit different way. Okay, very good question. I don't want to go into the details of DRAM as much right now, but yes, okay. Yeah, exactly. So basically, you have sense amplifiers on both sides, essentially, and you do the sensing in different ways. We'll get to that when we talk about clear DRAM. So I'm saving that to that part. But you don't need to worry about that. When you read the papers, you will see that better. So there's a lot of intricacy in DRAM. DRAM has been optimized for many years. So some of the ideas that may work for some architectures may not work for some other ones, or you need to engineer things better to actually make them work. So this idea off the bat may not work, but it's some other idea may work. Okay, we talked about Lisa, so I'm not going to go through this in detail, but I'm going to show you some of the benefits you get. Basically, if you remember, Lisa was targeting intra-subarray data moment, right? Inter-subarray data moment within a single bank, because there's not enough connectivity between the two subarrays. If you want to copy data from one subarray to another subarray, you have to go through the internal data bus. I don't know what happened here. Is this my fault or is this the computer's fault? I thought I fixed this one. Okay, maybe it's the computer's fault. But basically, what Lisa does is it provides a new substrate to enable wide connectivity between subarrays. And you saw this before. Oh, okay, there are two slides now. Maybe it is my fault. While trying to get rid of the bad slide, I made a copy of the bad slide. Redundancy. Okay, now the bad slide is gone. Okay. Now we have a lot of bad slides. Okay. Okay, basically, the basic idea is, maybe more slides are gone, I don't know. But you know the basic idea of Lisa. Essentially, the idea is to have isolation transistors between two subarrays. And you connect the row buffer or sense amplifier, sensing and pre-charge circuitry, as you can see over here, of this subarray to the bit line of the other subarray, as you can see over here. And you connect, you basically control that connection with isolation transistors. When the isolation transistor is turned on, the bit lines are essentially connected between the two subarrays, right? We've seen that before. And our goal was to really enable movement from one subarray to another subarray. And we have seen the benefits of this. Basically, we have this new command called row buffer movement. And the idea is to move a row of data in an activated row buffer to the next subarray over here. So if assuming that the data is all VDD over here, the bit lines, you activate the isolation transistors or enable the isolation transistors using this row buffer movement command, which means that the charge sharing happens between the top bit line and the lower part of the bit line. Now it's an extended bit line. And based on that charge sharing, the entire length of the connected bit lines become VDD, because this also amplifies the charge, as you can see. That's how you can transfer the value, okay? Okay, so this actually has more benefit. And I think we had a question in the previous lecture when I discussed this. How many subarrays do you connect using this isolation transistor? And we actually have a lot of analysis in this paper regarding this. And I think we decided we connect at most 2 using a row buffer movement command. And if you want to do more than 2, then you do another row buffer movement command from, so basically you could move the data from subarray 1 to subarray 3 with a single command. And if you want to move it from subarray 3 to subarray 125, you need to do many row buffer movement commands, essentially. So if you actually do if you actually do a single command, you can move from 1 to 3, as you can see over here. And the paper has analysis of why we decided that way. But basically, this gives you a lot of bandwidth, internal bandwidth. So outside bandwidth coming out of DDR4 is relatively low. This has been increasing, but now you can get more than 25x bandwidth, internal bandwidth for this data moment. That's the beauty of adding interconnects inside DRAM, as you can see, right? This is something that I think we should be doing better, because one of the problems with both moving data inside DRAM and also doing computation inside DRAM is the low connectivity, right? If you have low connectivity, it's very hard to do data movement, which is really needed for both data copy as well as communication across different units that maybe do computation inside DRAM. And this, I think this needs to, in a sense, DRAM needs to be rethought for this purpose, right? It was the original purpose of DRAM was to read data, right? If your goal is to read data, maybe you don't need these interconnects, right? But if your goal is to copy data and all move data where computation is done in one subarray and you want to move the data to some other subarray, you need better interconnects. Okay, there's of course DRAM chip area over it, and you can read the paper. So this enables multiple things that reduce latency. Clearly, we've seen copy. You can reduce the copying overhead, which is essentially the same thing as row clone, but now row clone happens across subarrays, which is good. And we basically see significant reductions in row copy latency and row copy energy. That's good. But there's also another benefit to this, which is kind of similar to tiered latency DRAM without some of the disadvantages of tiered latency DRAM. Without even going into open bitline architecture, you will see that. Essentially, we have long bit lines, we have short bit lines. Clearly, we've seen this trade-off earlier. Short bit lines are good for latency, but then it comes with a high area overhead. So the key idea of using the Lisa substrate for caching is you can add fast subarrays as a cache in each bank. So as opposed to partitioning a single subarray like tiered latency DRAM did, tiered latency DRAM partitioned a single subarray to a fast portion and slow portion, right? Now we're going to do something different. We're going to have a slow subarray. We're not going to change that. That's good for capacity. But we're going to add a fast subarray next to it, let's say. And the goal of this fast subarray would be caching. That sounds good enough, right? And you can still employ different kind of caching policies, exclusive, inclusive, operating system mapped, and you just use this and magically. And in the good news here is if you just use this and not change anything, including caching, etc., you will still get benefit because some data magically goes to the fast subarray. Does that sound good? So that's now we're overcoming a disadvantage of tiered latency DRAM, as you can see, or multiple disadvantages actually. So, but that's the idea over here. And the reason you can do this is because you have isolation transistors between the slow subarray and fast subarray. So you can actually take the data from the slow subarray and move it to the fast subarray, right? But even if you don't have that, if you have a heterogeneous design that looks like this, you can still gain performance. But that's the idea of this other paper, this Son plus Iska paper. So that's not really the contribution of Lisa. The contribution of Lisa is really ability to move data quickly between the slow subarray and the fast subarray. Yes?
Is the programmer exposed to the fact that this data,
Exposed to the fact that there's fast subarrays?
Well, when there is data in the fast subarray, was the intention of the paper to also expose that? Because
to the programmer.
To the programmer, because the programmer knows X address, and that X address was in the slow subarray, it was then moved to the fast subarray.
Yeah. I mean, normally the programmer doesn't get exposed to anything like this, right? But if the programmer somehow knows which data is latency critical, or which data is frequently accessed, which data could benefit from caching, they could use hints, assuming it's available. They could use pragmas in programming languages to say, okay, I expect this to be latency critical, assuming those are available to the programmer and they get communicated to the hardware architecture, right? But that's not what we discuss in the paper. What we do in the paper is really caching transparently to the programmer. But I think if the language provides mechanisms to the programmer and the programmer really understands what they're doing and they can correctly identify what is latency critical, assuming that information is communicated all the way from the language to the hardware, then I think it could actually, the substrate can take advantage of it, certainly. Yes?
Does the same address map to the fast subarray? Like, for example, if I wanted to access something, and it was moved to the fast subarray, does it have a separate address space area?
So that's a design choice, basically, right? That's what I meant by if this could be exclusive, meaning the addresses are not replicated, or this could be inclusive, meaning the addresses are replicated, and fast subarray is just a cache. But fast subarray can be part of main memory also. Yeah. This is very similar design choice as TLDRAM, except this overcomes a lot of disadvantages of TLDRAM. Yes?
What do you think would be the advantages of this? Because it seems like it's essentially just a lot of linear memory hierarchy where we have a bit faster memory for a bit higher cost, which we can access for like try to exploit temporal and spatial localities. And what would, for example, be the main advantage of this instead of adding, for example, an R3 cache over?
Yeah.
It's also just basically adding another layer to the memory.
Yeah, I mean, that's a very good thing to think about. Basically, I mean, there are multiple answers to this. One is, if you're using this as main memory, it's not just another cache, right? So if basically part of your main memory is much faster right now, right?
Essentially, yes, it's still what could data that you expect to access more frequently and to access faster to, which is latency critical into this memory area, which is essentially what a cache does.
Not necessarily. Imagine you didn't do anything, and 30% of your main memory is fast subarrays. 30% of your data access faster. Think about it that way. Right now, all of your main memory is slow. We're making 30% or whatever fraction that you want to add and that you can pay for, let's say. It's magically faster, right? It's not magically, of course, but you see the difference, right? If this is used as main memory, it has nothing to do with caching. Your main memory is fundamentally, its latency is reduced. Now, if you want to take advantage of that, yes, you're going to exploit locality. But then you can also do, you also need to do that when you're actually doing page replacement, for example, right? So think about all of this locality is currently done in the bigger part of the memory hierarchy. If your memory is not enough, for example, you also need to decide which pages to replace to the SSD. So you're already doing some page replacement and locality management in your main memory. We just want to do it a little bit better. And then there's a second answer. So this is one answer, which I think answers your question. But the second answer is very interesting, I think, because this is a different kind of locality exploitation than the adding caches to the processor side. So if you look at the processor side, you don't have caches that have such large blocks. The blocks are 64 bytes, 128 bytes. So locality is at that very small level. So this is a different kind of locality, which is really that large block locality, which many people do not really deal with when they add caches. So it's good to think about. So that's why I think the mechanism to exploit the locality over here need to be a little bit more tailored to these large blocks. That's why we see also benefits from this. Okay, so I think I've already given you the idea, but these are very good questions. Keep them coming. Essentially now cache rows, basically what we did over here is by adding isolation transistors, we can quickly move data from the slow subarray to the fast subarray. Okay. And we found out that this reduces hot data access latency by 2.2x, which is significant compared to not reducing it, let's say. Okay. If you're interested in this, I would recommend reading not only the TLDRAM paper, which is a precursor to this, but also this other paper, because this other paper is interesting. It was at ISCA 2013. It basically proposed this heterogeneous subarray architecture, but it didn't have these connections. Meaning, if you want to really exploit that, you had to do the data moment through software in some way. So it was actually very expensive to do that data moment, or you got to be lucky a little bit. But this data moment actually, this fast data moment capability between subarrays actually enables a lot of things. One more thing it enables is pre-charge latency reduction. So if you look at this conventional DRAM, normally how you do pre-charging is you really pre-charge the different bit lines from one side. And the pre-charge time is really limited by the strength of one pre-charge unit. Now, with Lisa, we can do linked pre-charge, meaning because the pre-charge units of the top subarray can be connected to the pre-charge units, to the bottom subarray, when you enable the isolation transistors, you can basically use two pre-charge units to charge a single bit line. We call this link pre-charging. And we actually see that you can get significant reduction in pre-charge latency, about 2.6x. This is actually very interesting also. Now you increase connectivity, but you actually get additional benefits. And this works with open bitline architecture also without going into the details at all. Okay, so there's more on Lisa. And again, I think apart from the specific mechanism that this paper proposes, I think maybe an even larger benefit is really thinking of the DRAM architecture. Like we're not thinking of the DRAM architecture as something that is designed for reading, but it's really about connectivity. And I think we really need to do more work in this area to enable better connectivity. Okay, let's see how much time we have. Maybe we should take a break. So let's take a break until 15:28, and then we're going to continue our exploration of different ideas. Or maybe it'll die after you discuss. Is it time? Did we say 15:28 or 29? I said 28. Okay, this is important for predictable performance. But it's 29. It says 29 now, so we can get started. So okay, I'm going to cover some more ideas that are interesting, I think. And I think this field is really important for developing new ideas, new creative, innovative ideas. Let's take a look at some of them. So we saw how Lisa overcomes some of the disadvantages of TLDRAM. But this work actually makes TLDRAM a little bit more practical, as you will see. And then we'll see another work that's actually also interesting. So this work proposed a very simple idea that could be used for multiple purposes to reduce access latency, refresh overhead, and also RowHammer vulnerability a little bit. So we already looked at conventional DRAM, right? The idea of copy row DRAM is basically partition the subarray into two types of rows, regular rows and copy rows, but not have isolation transistors between them. So we get rid of the isolation transistor cost. And this picture has a mind of its own. I should have turned off the animations. But basically, you have two parts, regular rows with a regular row decoder and copy rows with a copy row decoder. Essentially, the idea is copy rows can store the copy of any row in the regular row. But you have two separate decoders without isolation transistors. So how do you get reduced latency? We'll see that. So if you identify that so you can do a row copy operation, basically. If you identify some row is frequently accessed, you can basically copy it to, I don't know what's going on, but we should really disable this sort of automatic animations. Let me see. I really dislike my presentation having a mind of its own. Anybody want to help me here? Slideshow. No, it's not doing that. So how do you set up an automatic animation? Okay, I see. Yeah, okay. I'm not going to do that right now then. I never do that in my presentations. This is Hassan's fault. It's his slides. And I had this problem before. Yeah. I'm talking right now, yeah, as you can see. Well, he's not talking, he's acting. Yeah, but the animation is acting. But the basic idea is basically you can copy a regular row to one of the copy rows. Okay, and you know how to do this through row clone, right? And we use essentially the row clone. But now how do you get lower latency for that row? Basically, you use multiple row activation. You activate both copies of the row, and then that leads to lower latency because now you actually share more charge that essentially enables faster sensing. That's the idea over here. It's a clever idea. You could actually have more than 2 copies, as you can see, assuming you copy the same row multiple times. Does that make sense? You're really driving the same bit line with 2 copies of the same value. You can think of it that way. Okay, this gets rid of the isolation transistors, but clearly this doesn't have the power benefits of TLDRAM, right? It actually has more power because you have multiple row activation. Okay, so there are multiple use cases of this. One is caching. Obviously, you could use those copy rows of caching, like I showed. You basically cache frequently accessed rows, for example. Or, I've already said this, I'm not going to go repeat this. Basically, it's very similar to TLDRAM. You could also do reduce the refresh overhead. So, for example, you profiled your DRAM and found a weak cell in one of these rows. You could map it to a strong copy row and always access the strong row, right? This way, you can actually reduce the refresh overhead in a different way. You remap a weak row to a strong row. Strong rows means you can retain the data for longer, and then you can reduce the refresh rate. Assuming you can remap all of your weak cells, maybe you can reduce the refresh rate completely in all of your DRAM, right? Make sense? And then there's another idea. Okay, I think I already said this. So you basically access only the strong row. Of course, this requires modification for remapping, a remapping table for the copy rows. And there's a mechanism that we discussed briefly to protect against RowHammer. And the idea over there is if you detect a row being attacked in the regular row space, you basically copy that row that keeps being activated to the copy row space. That way you limit the damage someone can do to the regular rows, which is also interesting, as you can see, right? I think this is maybe a heavy-handed solution to RowHammer because you're moving data, but maybe in some cases it has some upsides. Does that make sense? Okay. Okay, so without going into more detail, this also provides benefits. If you actually combine the caching use case with the refresh use case, which the paper analyzes both individually and together, you can get significant speed up and DRAM energy improvements. And DRAM energy improvements are coming from both lowered execution time and getting rid of refreshes. It comes at a cost in hardware overhead, DRAM chip area, because now you have 2 separate decoders. For example, you have the multiple row activation circuitry. And also DRAM capacity loss because you're using this for copy rows exclusively for different purposes as opposed to as part of main memory. And also you need to modify the memory controller. So all of these ideas require modifications to both memory controller and DRAM, as you can see, right? At least. If you're exploiting something like this at the operating system level, then you need to actually change the operating system, et cetera, as well, as we have discussed. So this is another idea, as you can see. So this is lower cost, but maybe it's not, it's also more versatile, potentially. Any questions? Okay. I'm going to discuss one other idea. This was developed by Hao Song while he was an intern with us. Now he's doing his PhD. He's also worked on RowPress, as you guys probably know, and RowHammer too. Is he around? Or is he on Zoom? Okay. But basically, the idea here is very interesting, I think. Basically, we want to have some configurability in DRAM in terms of capacity latency trade-offs. So no DRAM really enables this in a configurable way, and we wanted to have it in a nice configurable way. Essentially, workloads may have varying capacity and latency demands, and the previous architectures that we have seen and the commodity DRAM make static capacity latency trade-offs at design time, right? For example, it's true for also tiered latency DRAM, right? Tiered latency DRAM has a static part that's near segment. Can we change that dynamically is a good question, basically. Essentially, our goal was to design a low-cost architecture that can be dynamically configured to have either high capacity or low latency at a fine granularity in the granularity of a row. And I think we should be thinking more and more in this sort of configurable memory direction, because this has actually implications for also processing inside memory as well, in my opinion. But basically, you should be able to, the goal was to switch a DRAM row from being a high capacity row to maybe slightly lower capacity but low latency access low. And to be able to do that, we're going to use the idea of replication. Basically, we're going to replicate the same cell twice, for example, and then sense both of the cells. So I'll give you the idea. So essentially, I already said this, a row can dynamically switch between high capacity mode to high performance mode. And the idea is to dynamically configure the connections between DRAM cells and sense amplifiers in the open bit line architecture. And this is where I will introduce the open bit line architecture pictorially. It's going to be a little bit different from what we have seen so far, which was the closed bit line architecture. So this is what a lot of modern DRAM looks like, because cells have become so smaller and sense amplifiers have become too large. As a result, what happens in a single subarray is one bit line is sensed by a sense amplifier on the top. The next bit line, consecutive bit line, is sensed by the sense amplifier on the bottom. And the reason it's called open bit line is you can see that this part of the bit line is open. It's not connected to anything. And this part of the bit line is also open. Make sense? So essentially, each bit line is connected to only one sense amplifier in this case, which is a good trade-off in terms of packing a lot of cells and sense amplifiers together. And still, that you need to do a lot to make it work. Okay, so the idea in clear DRAM is to make these connections between the bit lines and the sense amplifiers configurable. And configurable is essentially enabled by isolation transistors. In this code, we call bit line mode select transistors. And there are two types of these. If you enable only type 1, for example, it looks exactly like the open bit line architecture, right? Now, if you enable type 2, it's a different open bit line architecture. If you enable both type 1 and type 2, that's what we're going to take advantage of. Okay? That's the idea. So clearly, this comes at an additional area cost because you don't have just wires over here, but you have isolation transistors. But that's what gives you dynamic configurability, or even if you ignore the dynamic, it gives you configurability, right? Okay. So how do you get to the max capacity? You know what? Max capacity mode is essentially nothing different from existing open bit line architecture. We enable only the type 1 isolation transistors. And this mimics exactly what we do today in open bit line architecture, right? Okay, that's not that interesting maybe, but you get the same stored capacity. Clearly, you lose a little bit density because you have these isolation transistors that are extra. And then there's more modifications that you need to do, but that's in the paper. How do you get to high performance mode is really the innovation and the interesting part, I think. Basically, you can see that we enable both type 1 and type 2. But in order to take advantage of it, we actually store the value in one of the bit lines or one of the cells, and the complement of the value in another one. Now, what this enables is, if you these are called coupled cells. If you activate these cells, now you can actually do better sensing, better differential sensing through a single sense amplifier, or maybe both sense amplifiers. So you could actually use both sense amplifiers potentially. But basically, you can operate these cells or do the sensing much faster because you drive both of the bit lines and enable sense amplifier with differential values. And as a result, sense amplifier does the sensing much faster. That's the idea. And there's a lot of circuit level evaluation in the paper that you can see. So the sense amplifiers are also coupled, and this actually increases the sensing capability. It's similar to like pre-charge coupling that we have seen, right? In LISA, we coupled the pre-charge circuitries. Here, we're actually coupling the sensing circuitries and taking advantage of the two different values stored next to each other. Of course, the difficulty is how do you get the two different values stored? So you need to populate these things. But maybe there needs to be more future work in that area. So this enables reduced latency as well as refresh overhead via this coupled cell plus sense amplifier operation. So, okay, I'm not going to go into a lot of details to actually test this. You need to do a lot of circuit simulations, which are in the paper. But these are some results based on some of those simulations. And these are the values that we see, that we report in the paper. You can reduce essentially all interesting latencies: activation, restoration, pre-charge, as well as write recovery latency. Because having these strong sensing and strong sensing circuitry that takes advantage of coupled cells and coupled sense amplifiers really enables faster everything in the operation. And also there's refresh. Clearly refresh is affected because it reduces the latency of activation and pre-charge rate. And but the paper also evaluates some system level approach, and it shows significant benefits. So I believe that's actually an interesting idea in an interesting direction. There should be more work in this area. And maybe you guys will come up with different ideas in this direction. But this is a different way of thinking if you think about it. It adds more configurability into the bit lines. And it's also, it can be employed in conjunction with other ideas, right? Lisa, for example. Lisa is orthogonal. You can have another isolation transistor to connect with the next one. Any questions? Yes. You have your, yes. When you're in yes. Basically, when you're operating in high performance or low latency mode for a given row, you halve your capacity. Yes, but that's a very fundamental trade-off you cannot get away from. That happens, for example, in a sense, it's kind of similar to single level cell and multi-level cell in Flash that we will see, right? If you want to be low latency, single level cell is unbeatable because you just sense a single voltage reference. If you want to have high capacity, you pack more bits and have more voltage levels in the same voltage range, but sensing becomes more complicated, which means that it's going to take extra time. In a sense, it's very similar, except it's using two different cells as opposed to a single cell to store the same value. Okay. Okay, I think there's more work to be done in this area. Maybe Ataberk is thinking of much better ideas now. Or maybe other ones, who knows? Yeah. Okay. If there are no questions, I'm going to cover SALP a little bit because I think this is such a fundamental concept that should be covered. It also makes for a good story. But this is one of the earliest ideas we developed when we are actually looking at DRAM. It's called Subarray-level parallelism. I've already given you the key idea actually when we talk about refresh access parallelization, but SALP actually is much broader than that. It's really access parallelization, assuming those two accesses go to different subarrays. Okay, basically, we target bank conflicts. Whenever two accesses go to the same bank, today you serialize them. This is bad for performance. It's also bad for energy. It also thrashes the row buffer, as a lot of busy wait, etc. So our goal was to reduce bank conflicts without adding more banks, essentially, to do this at low cost. And it's basically this idea takes advantage of the underlying DRAM microarchitecture. A bank is not a monolithic structure. It really consists of subarrays, as we have seen earlier. And each subarray has its own local row buffer, local sense amplifiers, essentially. So this is our old picture that shows logical bank looks like this, but really physically, a bank is divided into a bunch of subarrays, okay? And each subarray looks like this kind of ugly picture, but it has a local row buffer, as you can see. Each subarray is like that. And then there's a global I/O circuitry, which we call row buffer, which we should not call row buffer going into the future, but that's how it is. Okay, so the second key idea, after you observe this, is to see that the subarrays are actually mostly independent. If you look at how these subarrays are organized, you have a global row decoder that's shared, and then after the address is decoded, this subarray operates independently, mostly. There are other global structures, which is the global I/O circuitry, global bit lines, basically. We will see that in a little bit more detail. So these are the shared structures. Everything else is mostly independent. The key idea is, can you actually reduce the shared global structures so that actually you can access subarrays mostly independently? Today, what happens is you cannot access one subarray while you're accessing another subarray. Now, that's not exactly true. Later work by Giray showed that you could actually do that, right? In a limited way. But we wanted to do in this work, like 10 years before Giray, showed that it's actually possible, or part of it is possible in real DRAM chips, is to actually do this by modifying the DRAM so that we can actually access two subarrays mostly in parallel. Okay, so basically to do this, you need to really reduce the sharing of the global decoder to enable almost parallel access to subarrays. Basically, you need to be able to activate two rows in two different subarrays, at least two different subarrays. But a global row decoder that's shared between the two subarrays doesn't allow for that, right? Okay, So you need to do some latching, perhaps, right, as we will see. A global developer doesn't enable reading from two subarrays concurrently. We're not going to do that. That's expensive. But we're going to try to reduce the sharing on the global I/O lines so that while we are reading from one subarray, we don't disturb the other subarray, essentially. Or put another way, we want to reduce the connection of one subarray to the global bit lines while we're reading from another subarray. Okay? These are the two basic ideas. So let's take a look at how these work. So this is, two different subarrays over here. Both of them are local row buffers, and then there's global I/O, and then I'll show you the global bit lines later. Let's take a look at how we reduce the global decoder. Normally what happens is you decode the address, and then you have a latch over there. There's a global latch. But this global latch drives all of the subarrays, as you can see. So in order to activate two subarrays concurrently or consecutively, we just need to have local latches. A little bit more expensive, but it enables activation of two different latches, two different subarrays. Makes sense, right? So in one cycle, you send the address to this subarray. In the next cycle, you send an activation to another address or another row in another subarray. That's the idea. This way, you can activate two subarrays concurrently, more than two also. Right? Okay, that's the idea. So we solved one problem. Now we don't have this global decoder sharing problem. The other problem is the global bit lines. So there are global bit lines that are running vertically, not as many as the local bit lines as we have discussed earlier. But these are the ones that take the data from the local row buffers and put it to the global I/O circuitry. So I'm going to show them in a different way over here. Normally, this is a logical picture. It's not a real picture, clearly, right? You don't have global bit lines outside, not touching the array. But to demonstrate how these are really connected, normally what happens is whenever you send a read command, you take the data from the activated local row buffer and take it through the global bit lines. Makes sense, right? But there's no switch normally between these global bit lines and the local row buffer. What you bank on is only one row in one subarray is activated today. If that's the case, you're guaranteed that only one local row buffer will drive the global bit lines when you get a read command. But now we're violating that. We have at least two activated local row buffers. Now, if we get a read command, we need to decide where to read from, first of all. But assuming we read from one of them, we should be able to supply the data from that particular subarray or local row buffer to the global I/O. To be able to do that, we need additional connectivity, meaning switches. So that's what we add essentially. So we have a designated latch to designate which subarray we're going to read from. And assuming that we're going to read from this subarray, this designated latch connects the switch. Normally, the switch is open, meaning whenever you activate, you don't immediately connect the column over here to the global bit lines, and none of them are connected. Okay, but when you actually do a read to a particular subarray, you set the designated latch, and then you connect the data from the local row buffer to the global bit lines. Makes sense, right? The column that you're reading. That's the idea. And then if you want to read data from another subarray, you deactivate, meaning set the bit of this designated latch for this blue subarray to 0, switch is disconnected, and you designate this subarray to be connected to the global bit lines. Makes sense, right? So there's some switching overhead, clearly, subarray to subarray switching overhead. So you need another timing parameter to enable this. But it's much better than pre-charging the entire bank, activating another row, and then reading, right? So that's what we're saving, basically. If there's a bank conflict, and if the data is mapped to two different subarrays, now as opposed to, and imagine a bank conflict where you keep reading from the blue one and the yellow one consecutively. Blue, yellow, blue, yellow, blue, yellow, blue, yellow, blue, yellow. You would be incurring the TRC delay for all of those accesses. You need to essentially pre-charge and activate, pre-charge and activate, pre-charge and activate. Now, we reduce that to only switching delays, right? What happens is essentially you activate blue, activate yellow, they stay activated. Assuming your access pattern is such that you do blue, yellow, blue, yellow, blue, yellow, what you do is basically you just incur the switching penalty. which is still some time, but it's much, much lower than pre-charge and activate for sure. So it's a very low latency switching. I like this idea a lot, as you can see. Other people like the idea a lot too. But of course, it comes at a cost, right? The cost is you need to have per subarray latches and these designated subarray bits. Switching is already kind of there actually, except we don't talk about it. Okay, so basically, this is the baseline bank organization. Essentially, in the baseline bank, this is how we change it. You distribute the global latch to local latches, and we add designated bits over here. And then also the switching capability, such that this designated bit connects, controls the connections from the local columns over here to the global bit lines. And there's some overheads. Maybe we underestimated the overhead a little bit, but doesn't matter. It's very tough to get these overhead numbers, but that's how it is. Okay, so results. Let's take a look at this. The paper has a lot of results. The paper has actually 3 progressive mechanisms. One of them is very similar to what Giray kind of did, but not exactly with a refresh. And we see significant dynamic DRAM energy reduction because you actually reduce the row buffer switching, open, close, activate, pre-charge, etc. And row hit rate also improves because now you can actually service things from different subarrays and you keep them active. And we also see significant system performance improvements. So these are different types of SALP. Some of them have very low overheads, but low benefits. The let's say most aggressive version is multiple activated subarrays, which is what I just described. It gets you almost the same performance as having the same number of banks as subarrays. But having the same number of banks is very expensive because you need to actually replicate the decoder circuitry across many of them. Okay, so you can see that having the same number of banks as subarrays is actually a 36% area overhead. Whereas even if you think that we underestimated the area overhead over here, it's 1%, maybe 2%. If you're terrible at designing, maybe 3%. It should not be 3%, I think. But DRAM manufacturers sometimes exaggerate how much their design effort is. I think everybody in industry exaggerates their design effort in general. They don't want to change anything. If you can make money without changing anything, that's the best mode of operation in industry. Terrible for progress, of course, right? Okay, I'm joking, of course, but yeah, terrible for also staying in business in the long term, I think. Okay, so more on SALP. This is the paper. But the good news is immediately these Samsung and Intel folks picked up on our paper. They actually did their own simulations. And they basically said, we should use the SALP. And one of the reasons they said it is not necessarily because of like this whole package that we come with SALP, but because they basically said write latencies are increasing. We can relax the write latency to make the design much better, meaning much robust. Because if you don't relax the write latency, you start getting errors and you need to add additional ECC, etc. But if you relax the write latency, make it longer, now you can actually use Subarray-level parallelism to overcome the increased latencies. So you can tolerate the increased latencies. And that's what they show. That's what they evaluate on their performance simulators. And they basically say with SALP, they get much better benefits, which is nice, right? You can read the paper for more detail. They have a paper and they have a presentation also. Okay. So why did people not implement this yet? So these two companies actually pushed for the adoption of SALP and DDR4 extended standard at the time. Unfortunately, they lost the political game, even though they're two major companies, Samsung and Intel, right? We're talking about two companies that don't normally talk to each other, but they wanted the same thing in this particular case. And they verified a lot of these things that we said in the paper. Yes, our overheads are a little bit underestimated, but they still think this could be doable easily. But unfortunately, they were not able to convince the political voting body, which is in the JEDEC standards, at least at the time. Who knows, maybe this will come up again. But essentially, they got outvoted because people didn't want to change. So you could have a much better DRAM with Subarray-level parallelism today if that vote went the other way. So you can blame. This is one of the reasons why I actually think these standards bodies are actually against innovation in general. They're innovative ideas, and there are people who realize that ideas are innovative. They independently verify the ideas. This is all done completely independently of us. We didn't touch any of the simulators. They actually wrote the paper and discussed with us afterwards. And it's also published. You can find it. So there's clear innovation over here, but a standards body is made up of so many, let's say, companies that don't necessarily, the goal is not necessarily innovation, right? Some of them have ulterior motives, clearly. Many of them have the motive of making money. And some of them have very low margins, so they don't want to change the memory controller, right? So there are memory controllers that don't want to change the memory controller. There are memory companies that don't want to change the DRAM. And if you're in that situation, innovation gets squashed. So hopefully this gives you a good story of how innovation sometimes doesn't get adopted, right? So you may have a great idea, but it may not get immediately adopted. It may take some time, but I believe that this is actually a good idea. It will at some point get adopted. We'll see how long it'll take. Yes?
Giving a separate DRAM command to match the data from...
Yes. Yes, basically we add some separate DRAM commands. We try to minimize the changes to the interface, but you do need some commands, yes. But in the smaller versions, like if you look at over here in the paper, we have SALP1, SALP2, MESA. Some of them have even fewer commands. I'd recommend reading the paper. And I think actually the version that these folks evaluated was not the most aggressive version we proposed. So even with the, let's say, not so aggressive version, they got significant benefits. Okay. I think this brings us to the end of the lecture. I'm happy to take questions, but given that we have a time slack of only 3 minutes, I don't think I'm going to cover any ideas. But I should tell you, maybe I'll tell you this. Unless there are questions, I'll just give you one slide overview of this, and then we can part. Okay, basically, we're going to tackle the one-size-fits-all approach to latency specification. So in the earlier part, we talked about how to change our thinking of the DRAM microarchitecture to reduce latency. Now we're going to talk about not changing the DRAM microarchitecture necessarily, but getting rid of the inefficiency we have. Basically, a reliable operation latency is actually very heterogeneous. There's not fixed latency. Temperatures, chips, parts of a chip, voltage levels, they all have different reliable operation latencies. And the general idea in the works that we're going to cover is to find out and use the lowest latency one can reliably access a memory location with. Ideally, you would do this dynamically, as we will see later. But you could potentially do this statically also. And we're going to cover a bunch of ideas that try to do this across chips, across temperatures, within a chip, within different parts of a chip, within voltage levels, and also use the idea of reducing latency for some other purposes like true random number generation, etc. But to be able to do this, you would like to really find the source of latency heterogeneity and exploit them to minimize latency or create other benefits. That's the idea over here. Like, why is latency heterogeneous? Again, we're basically a process manufacturing variation. You have different manufacturing and operation conditions. So this leads to latency variation in timing parameters. This leads to latency variation across chips. Some chips may have very strong cells that can be accessed faster, reliably. Some chips may not have those strong cells. So you need to actually access them a little bit longer so that the circuit settles and you get the correct result, right? And even within a chip, there's some distribution. This is, of course, not exactly like this distribution, but there's some distribution. Some cells are strong, some cells are weak. So what DRAM manufacturers do today is they specify a fixed latency. They don't take into account any of this. Basically, they try to specify a standard latency so that almost all DRAM chips that they manufacture is acceptable. Why? Because this is good for business again, right? Yield. If actually DRAM standard latency was somewhere here, lower, a lot of chips would not be acceptable. As a result, you would make less money. There could be some binning that you could also do, actually. That's done with processors, but we can talk about that later. Okay, so we're going to see how we can actually take advantage of this heterogeneity. Not necessarily. We will see that. Yeah, you can do other things on top, to enable predictability. Okay, I'll see you next week. Have a nice weekend.